So, we are talking about the etching solution, anisotropic etching solution of quartz. So, one of the etching solution used for micromachining quartz is hydrofluoric acid. HF based solutions are normally used for etchant, used as etchant for quartz micromachining, and for that we use chromium gold as a masking material, chrome gold. Now, one of the problem we face if we use only hydrofluoric acid is that it gives you some kind of crystallographic facet or kinks at the surface, and if lot of facets and kinks are produced, then the irregular structure of the quartz crystal will not be produced. In that case, if you use at a vibrator or the resonator, its frequency of oscillation or resonance frequency will change, because resonance frequency of that crystal microstructure depends on its shape. Okay. For that reason, we need the micromachining with regular feature, vertical side wall and lateral structure without any facet or kinks. For that, another etching solution is used, that is ammonium fluoride NH4HF2, and if you use at low temperature etching, then etching will be very slow, but you can get rid of these crystallographic facets or kinks. So, let us see what are the kinks that produce in case of first etching in hydrofluoric acid at higher temperature. So, here two crystals are shown. In the A, you can see here this is the masking layer. So, this is the masking layer here produced here, this is the masking layer. So, now it is going to etch here. So, you get here some kinks. So, this is the kink, here this is the kink, or it is known as the facet. It is because of the regular structure of the crystal, that is quartz crystal, it will produce like that. So, this kind of things will disturb in your performance if you use that the kinked structured quartz in your piezoelectric sensor. Performance will be a lot of deviation. Now, if you use another etching solution which is saturated ammonium fluoride solution, if you use it, this solution, then you see in the left side B curve. So, this kinks and facets has reduced into a small one. Here it was large kink, here it is small kink. And now, at the same time, if you go for low temperature etching, then those things almost will vanish. Low temperature etching, the etch rate may be very slow. So, you have to allow longer time etching, and but you can get rid of this kind of the problems which deviates the performance, which are really problematic in getting actual resonance frequency of the structure, as well as if you use that resonator in any of the tank circuit, their Q value will not be very high. Okay. Now, here what are the etching solution that use NH4H. So, the HF we take some amount, then NH4HF2, the ammonium fluoride plus H2O, and etch rate has been found at 22 degree centigrade, means room temperature is 6 micrometer per hour, and if you do the same etching at 80 degree centigrade, it is 16 micrometer per hour. So, that means automatically room temperature etching is very slow. Chromium etchant to use, because masking material is a chromium gold. So, you need etching gold as well as chromium also. For chromium we use ferric ammonium nitride plus perchloric acid plus water. So, ferric ammonium nitride perchloric acid water mixture that will etch chromium with an etch rate of 100 angstrom per minute at room temperature, that is 22 degree Celsius. Then gold etchant we use here, standard iodine based gold etchant from Tanzin, USA, that is one supplier who can supply lot of chemicals which is used in etching of different kinds of materials. So, we have procured that gold etchant, that is iodine based gold etchant, and their etch rate at room temperature is 0.1 micrometer per minute. So, these are the etching solutions for masking material as well as quartz, which has been standardized in IIT Kharagpur, the quartz micromachining laboratory. Okay. So, those parameters little bit change depending on your temperature you use or depending on the chemical concentration you use, but overall principle will not change and the etch rate will be close to those values. So, in any of the laboratory, before you start any process of quartz MEMS, you have to standardize each etching step, either mask material etching step or quartz material etching step, that you have to standardize, then you can go for the complete MEMS fabrication process. Okay. Now, just we can conclude here that removal of kinks to get vertical sidewall is an important issue. 60% reduction of kink length from its initial value after dipping in quartz etching solution for 4 hours in at 80 degree centigrade. To get near vertical edge profile, the sample was dipped in etchant for 4 days at room temperature, kink was completely removed. That is very important. You can see here that kink was completely removed, but how much time you took? Nearly 4 days. So, that means etch rate is very slow at room temperature, you are using at room temperature. At room temperature for 4 days it will take. For the complete removal of the kinks and etching of the quartz is nearly say 50 angstrom or 50 micron or 100 micron, that also the time also depend on how much thickness wafer you are taking. Okay. So, that wafer which we are using in our laboratory, that is the 100 micrometer thick quartz wafer, and that takes this amount of time. Now, these are the some standardized for standardization you have to go for the etch rate measurement of for different concentration of hydrofluoric acid or different temperature of the hydrofluoric acid solution. So, with temperature the plot is here and with concentration the plot is here, from there you can choose your data. Now, these are the some of the structures which has been fabricated in our laboratory using quartz micromachining technology. This is a gyro chip with electrode connection, these are the electrodes. So, details principle of the gyro chip I will discuss in MEMS sensor lecture, not here. So, the structures I am showing here. So, you can see the white region things are the electrodes, here also gold electrodes are visible, micro beads are there, you can see the here thickness and here thickness of the quartz are different. This particular region, the thickness of the quartz is different compared to this region. This is thicker and this is the micro bead. So, here is one micro bead, here is another micro bead you have formed. So, one that means automatically you can get a step and metal line will go here, then step, then it will go down there, then it will go up, then again. So, that means this step over that metal lines will pass. So, that is a really is a tough and critical technology to make the metal electrode interconnection, but with lot of effort we are able to fabricate not only the quartz structure as well as the electrodes, and the results are also encouraging. Now, the another structures which we make out of the quartz sensor, that is the dual ended tuning fork. So, here you can see this is the quartz structure, and there are 5 pieces are there, and on that this glossy thing here is a metal. This is the gold metal you are using for electrode. This is a gold metal and this is also gold metal, and the shaded thing is basically the quartz, the whole piece of quartz, how it is etched, and is a basically dual tuning fork. So, tuning fork, all of you know, its structure is similar to that. Okay. Now, if you connect one tuning fork like this structure if you make, so you cut it here. So, here is one thing and here is another thing. So, that means is similar to that. This side is held and this side also held. So, if you cut separately here, so another one tuning fork here, another tuning fork here. So, there is a dual tuning fork is connected from this side. So, this will act as a resonator or this will act as an acceleration sensor also. So, the basic principle of the resonance or acceleration sensor will be discussed in MEMS device, MEMS sensor class, not here. Here just I showed you the structures which has been made in our quartz micromachining laboratory. So, with this the quartz micromachining I will not discuss more. So, I will now switch over to some other topic, and that is the various microstructure fabrication using the micromachining technology. So, those some of these structures already I discussed, and now I will continue some other microstructure which can be fabricated. Okay. Yeah. So, fabrication of micromachining microstructure devices. Few devices I mentioned in my last lecture. So, that is the micro velcro, the condenser microphone. Those are very simple structure, freestanding polysilicon cantilever beam. So, now I will go for a little bit complicated structure, MEMS microstructure, which is used as a device also, that I will discuss now. So, first one is a micro velcro, already I have discussed. Linear motion micro actuators. So, let us spend some time on this linear motion micro actuators. So, sensor can sense and actuator can act something, that we have seen. So, that means some kind of the attraction or some kind of repulsion kind of thing in a microstructure, if it does by applying some electrical signal. So, then it is called an actuator. So, similar thing can be made using the micromachining process and applying some innovative ideas. So, here is an example of the micro actuator, which is made out of the piezoelectric thin film, which is zinc oxide or PZD. So, here you can see the actuator uses folded path geometry. When a voltage is applied to the dual electrodes on the top surface of a piezoelectric thin film of PZD, the PZD either expands or contracts its length depending on the polarity of its voltage with respect to polysilicon layer. Where is the PZD material? In the black region, here is the PZD material. This is the PZD. You can see this is the PZD. You can use zinc oxide instead of PZD. So, now you have used some folded path geometry, that means some kind of structure folded path like this, it is coming here, here, then it is here, then it is coming here, then here, here, like that. So, you are increasing the length. So, you see there is another geometry is there. So, that is you can see it is coming like this. Like this. Okay. Now, one is the blue color and another is this one. Now, you see both of the structure vertically it's formed on the PZD or zinc oxide material. And now, one thing is that if the PZD or zinc oxide is a piezoelectric material, if we apply some voltage with respect to a ground plane. So, then what will happen? So, because of the inherent nature of the material, there will be some contraction. If it contracts, so then what will happen? So, if the film try to contract, the whole thing can be stretched because it is a folded structure, or it can be either stretched or it can be compressed. So, both are possible. The bottom is the polysilicon layer, the polysilicon ground plane, that is the polysilicon ground plane here, the hashed line here, this is the polysilicon ground plane. Now, if you apply with respect to the polysilicon ground plane positive voltage here and here negative. So, depending on positive and negative, you can change for actuation either contraction mode or is a repulsion mode, you can make it. So, that has been done here to get the micro actuator, and let us see how it can be done. The alternated expansion and contraction from one bar to the next and the mechanical series connection of the bars cause the net change in the length of each bar to add to that of the other bars. This cumulative effect permits a substantial increase in the actuation range of this type of devices. That is the basic principle. These two layers, you see this layer and this layer, either it expand or contract and length has been added. So, that the total it is connected in a series the bars. So, that you can get a substantial amount of increase and contraction. So, that complete thing, the whole structure can some mechanical movement you can get from the structure. So, that is the objective of that. So, now these are the process steps, how do you make it. So, what are the first step? First step is the deposit and pattern sacrificial layer, deposition and pattern of the sacrificial layer silicon dioxide. So, that is the silicon dioxide layer, first we made it. Then deposit and pattern of polysilicon. So, you just polysilicon made it and then you pattern it. Okay. After making the pattern, then the PZD film, the black one is a PZD film, deposit PZD film, then you pattern it. This oxide is a sacrificial layer. So, if you remove it, so bottom thing will be whole. So, when you contract, so there will be space, so that it can get some space for movement. Bottom is at the end stage you will find. So, bottom is etched, then you will get some open space. So, that through that the movement is also possible. Now, here after the patterning of this PZD film, then you go for the electrode formation, because the black region is basically the PZD. Then on top of that you are getting the electrode formation. Yeah. Metal electrode formation, deposit and pattern metal electrode. Then last step here is the etch in hydrofluoric acid solution to remove sacrificial oxide and release the mechanical structure. You see this particular layer, which is oxide is not here. This oxide, complete oxide is removed. So, that you will getting, if you draw a line here, then there is a open space here. So, when it contract or expand, so whole structure may go down or it can go up, because you are applying electric field either here positive or here negative. This is the one electrode, this is another electrode. If you do like that, then the whole thing it can just contract, some mechanical motion you can create, and for that bottom you are allowing certain top there are obviously some space is there. So, bottom also you are allowing some space, so that when it goes down, so this kind of mechanical movement you can allow and it can get some space. So, this is linear motion micro actuator, which may be fabricated following the steps. Now, another example, now I will discuss a rotor on a center pin bearing. This is another mechanical structure which may be made using the micromachining technology. A rotor on a center pin bearing. So, a center point bearing will be there, a structure will rotate based on that bearing, that is used in many of the joints, links which I have showed in the introductory class on MEMS. Many such structure there you need lot of the bearings. Okay. So, there are a lot of rotation motion is also required in many of the micro actuators. So, how it can be made? Disc shaped rotor made of polysilicon, and that rotor is free to rotate about a polysilicon center bearing. Now, let us look into the steps. So, first this is the silicon material, you take silicon material and then you deposit oxide. This is the oxide silicon dioxide. On silicon dioxide you make some masking, you go for some masking layer and then you etch little group here, which is the bushing mold. Okay. So, after formation of that, then you go for polysilicon deposition and pattern, which will be your structural layer, because you are making the rotor using the polysilicon you are using. So, this polysilicon is deposited and patterned. Now, this is the case here, what is that is the bushing point and is the rotor point. Now, you have to make the bearing anchor. So, for making the bearing anchor, then again you have to go for deposition of some masking material, that is here you deposited, that is oxide silicon dioxide again, and then you pattern. So, you just get the space for anchor, this is the space for anchor. Bearing anchor place is open and rest of the region are closed with silicon dioxide. Now, what you did, again you deposit here the polysilicon. Okay. You deposit polysilicon here, then again you pattern it, so that a bearing structure is formed. Now, C, D, E are shown here. C is here. So, bearing deposition and patterning of second polysilicon structural layer, which defines the center bearing. So, the center bearing has been defined here. This is the definition of center bearing. Then release of the rotor by etching two sacrificial layers in HF. So, you see after that what you did, you release two sacrificial layer. One is this sacrificial layer, this portion, this portion, this portion and this portion. So, then if you remove that, so that means this is a bearing and this structure will be open, because you are removing this also, then it will rotate. Here you will get some hole, here you will get some hole. So, that means two free structure which can rotate like this and over the bearing, this center bearing is here, is okay. When you release that sacrificial sacrificial layer, the whole thing, the polysilicon, the center pin bearing as well as the side, the rotor are free now to move. So, how you will rotate it by how you will actuate the rotation, that is different story. Whether you apply some electric field or you join, you can make some metal and then using some just attraction or repulsion by using attraction or repulsion electrostatically, that is a different story, but the structure you can form like that by just the micromachining, means here we used again the surface micromachining process. So, this is the free rotor and center bearing. Okay. So, this is one kind of thing which you can make. Okay. Now, we can go for some other structure. Center bearing side drive micromotor. Center bearing side drive micromotor is a very complicated structure. Bearing is a central and side drive, and these are the stator. This is the stator, this is the bearing, these two are the rotor. So, this portion are the bushing material, this is the anchor is here. So, this is the bearing, this is a stator and this is also stator, these two are stator, and this will rotate with the rotor on the bush, and this is the bearing. This is a cross section view of the salient pole micromotor, and here is the top view of the salient pole micrometer. So, here these are the rotor and this is the stator, A, B, C, A, B, C, A, B, C, A, B, C. These are the stators, this thing and these things are same. Now, in the central is a rotor, this one and this one is there. So, 1 2 1 2 1 2 1 2. Okay. Now, the whole thing, the complete bearing surrounding that, and this bearing it will rotate, and for rotation the stator is there. In stator you apply certain field, you have to make some electrode arrangement. So, that the field will be more and more from A to B and B to C. So, that here if you apply the positive and here 1 and 2 is negative. So, this negative will attract towards the positive side. So, it will little bit movement in this direction, then again it is again much more field movement in this direction. So, once it started moving like that, so then it starts rotating if you apply the gradient field in that stator. So, that is the basic thing, and the structure is the cross sectional structure is shown in this diagram. Now, let us see how this can be made, steps. A variable capacitance side drive micromotor clearly requires electrically conducting materials for both the rotor and the stator. Highly doped polysilicon satisfies this requirement. Stator and rotor you need some conducting, because you are going to, this is actuated by using certain field. So, it has to be some conducting material. Fortunately, the polysilicon if you dope heavily, so that will work as a conducting material, because if you use some metal film, so their stability will be less compared to polysilicon. Polysilicon stability is more compared to any of the metal films, either it is aluminum or some aluminum silicon or some copper or some other things. Okay. So, that is why they choose the doped polysilicon as a conducting material, and the rotor and stator are both made of doped polysilicon. The stator poles need to be electrically isolated from the substrate, the rotor and one, because stator and rotor they has to be electrically isolated. This is the stator, this stator and this rotor must be electrically isolated. This electrical isolation is achieved by LPCVD ground silicon nitride. So, this is one shield which is a with the separation, the LPCVD ground silicon nitride is used as a shield material which will isolate the stator and rotor. So, now process steps are shown here. What are the steps? First, they have used silicon substrate, then the anchor material for stator. What is that? That is 1 micron silicon dioxide plus 1 micron silicon nitride, that will be Si3O4 not sorry SiO2 and Si3 silicon nitride N4. Okay. So, silicon dioxide and silicon nitride here is a stator insulating anchor. Then after that what you did, the polysilicon shield you have made something here, then you go for first LTO, low temperature oxide. This is silicon dioxide, LTO means low temperature oxide. This material is basically SiO2. So, on that first LTO you just pattern it, so that you will get the bushing mold. So, this kind of bushing mold you can pattern here. So, this is the bilayer you have used here, the silicon dioxide and silicon nitride LPCVD ground, that is the insulation bilayer. Then you go for, because this silicon dioxide silicon nitride bilayer structure has been used to withstand high voltage, because a stator and rotor in between the voltage may go up to 250 volts. So, that is why the not only oxide and nitride combination has been used. Okay. So, nearly 250 volt you can get it, it can withstand, and after that you go for patterning other layers. Heavily doped polysilicon pattern to form the shield, that is completed. Deposition of first thermal LTO sacrificial layer and pattern for the bushing and stator anchors. So, that these anchors are here, stator anchor and here you can see here. So, deposition of 2.5 micron thick polysilicon and heavily doped with phosphorus. Polysilicon and heavily doped with phosphorus, then growth of 0.5 micron thick thermal oxide for etch mask, and polysilicon is patterned by RIE to form the rotor, stator and air gap as shown in figure B. So, here you can see. So, this is the thermal oxide here, and now the mask polysilicon there is patterned by reactive ion etching to get the separate, because here the total thing is there. So, this is this is LTO, but this is poly. So, now the poly has been patterned, so that now you can get the rotor and stator separately isolated. Okay. And in between the air gap, this is the air gap, this is the air gap. Then some air gap has been allowed here, because the polysilicon due to the rotation the temperature may increase. So, in that case you have to allow certain space, so that it can freely move. So, after that what has been done is a second LTO, after this the second LTO is there here, this portion is second low temperature oxidation is filled like that by CVD technique, and then you have to go for the sacrificial etching. Second sacrificial LTO which are shown there, the second sacrificial LTO is here. This provides 0.3 micron of LTO coverage on the rotor and stator sidewalls and 0.5 micron of LTO coverage on the top surface. The bearing anchor is then defined and etched through 2 sacrificial oxides down to the electric seal below as shown here. So, now the bearing anchor will be defined means it has to be sacrificial oxide which is formed by LTO, that is removed, then you will get this LTO sacrificial layer will be removed and you get the total structure here and here. Because if you remove this portion, if you remove this portion, this portion, this portion and this portion, and then you will have the free structure which will, this will be free, this will be free and this will be free after removing that. So, that is done in the next step here, and then the bearing material is deposited, 1 micron thick polysilicon layer and heavily doped with phosphorus, that pattern to form the bearing as shown in figure D. This bearing is formed at the end step and then you will get the complete structure here. The completed device is immersed in hydrofluoric gas solution to dissolve the sacrificial all LTOs and release the rotor as shown in figure E. So, this is the step by step. You have to give little bit concentration on each step, how the structure is formed by subsequent lithography and etching to get the ultimate structure. That is a side drive micromotor, and that picture you see many of the MEMS articles, the electrically driven micromotors using the MEMS surface micromachining technology. This is the process steps we use for getting such structures. So, now I will discuss another microstructure device, that is known as overhanging micro gripper, because many times you have to hold some small thing using some grips in case of actuator mechanism. So, that micro gripper particularly used in micro robots. So, there also whole technology is not so simple, difficult. Some of the salient points I just mentioned here, and if you look into the diagram, then again the actuation is basically done with the help of some electrical actuation basically. Now, here the micro gripper is made of polysilicon and it overhangs over a this is a gripper, you can see here this exploded of this portion is shown here, this portion is shown here. Now, you see here there are 3 structures. If you minutely look into the structure, there is central, there is a cantilever, this is one cantilever. Top there is a drive arm which is fixed with this. Bottom there is a another drive arm here which is fixed with this, and in the center there is a cantilever. Now, the basic mechanism is that you made lot of the electrode finger like electrodes are here. Now, you apply the field how you can apply the central the cantilever at certain potential, positive potential, and then the upper support and bottom support if you apply negative. So, then what will happen? They will attract each other. So, these are the electrode configuration. Now, when you attract, so this will go down and this also will go up, this will go up, say the upper and lower will be attracted by the middle one. When upper and lower is attracted by the middle one, then these things so you can see now, then this will go up and this will also go down. So, as a result of which here gripping will be there, it will hold, just electric field actuation. So, the total structure looks like this. So, this is a micro gripper. It consists of a closer driver, that is the closer driver is shown, and 2 drive arms that connect to arms that extend to the gripper jaws. This is the gripper jaws. this is one arm and this is another arm. Those are connected to a gripper jaw. This is a gripper jaw. Okay. So, now this structure how can you fabricate? That some step I will show you. The beam widths for the drive arms and comb teeth are 2 micrometer. This is the comb teeth, here it is shown, comb teeth, these are 2 micrometer, whereas that for the closer drive is 10 micrometer to provide relative rigidity. That is basically the closer drive is a 10 micrometer, width of this is 10 micrometer and this comb teeth are 2 micrometer, 10 and 2. So, that it will be much rigid. When a voltage is applied between the closer driver and the drive arms, closer driver and the drive arms move and close the gripper jaws. You are applying voltage, then the drive arms will move and is close the gripper jaws. The drive arms are kept at the same potential to avoid any current flowing between the gripper jaws, that is very important. The upper and bottom the gripper jaws. So, if they are on same potential, there should not be any current flow in within them, no current flow. So, that has to be maintained, and if there is current flowing through the jaws, so it can affect the actuation process. That is why these two are maintaining the same potential. Now, the tentative dimensions are shown here. The cantilever is approximately 12 micrometer thick, 500 micron long. This cantilever is a 500 micron long, 12 micron thick and tapered from a 400 micrometer width at the base to 100 micron width at the end. So, this is tapered. Here is a 400 micrometer and to coming here is a 100 micrometer. Here is a 400 and coming to 100. Oh. Okay. So, if you go like this, yeah. So, this is the final the form of the overhanging microgripper. Polysilicon microgripper is 2.5 micrometer thick and 400 micrometer long. Other dimensions are shown in the cross sectional view here. So, from here it is a 7 millimeter, 1.5 millimeter. So, from this point to 400 micrometer, from here this is millimeter, from here to here is a 400 micrometer. So, all the these are V group, this is a silicon die, PSG is a phosphosilicate glass, the support cantilever is here. So, this is a cross sectional view is shown here. Now, the process flow, how do you proceed? So, first they are taking a silicon wafer, then diffuse P plus region and remove the oxide mask and borosilicate BSG. After P plus, then the PSG, this is a phosphosilicate glass is deposited the insulating layer, the polysilicon, then the polysilicon is patterned. After patterning polysilicon, then you go for the deposition of the patterned polysilicon by RI. This RI polysilicon is patterned by RI in CCl4 plasma. At this step it defines the patterns of the gripper and the conducting lines. The polysilicon on the back side of wafer is removed subsequently. So, because when you deposit the polysilicon, it will be there in the back side also. So, after patterning this one, back side polysilicon is completely removed. Then we come to this structure. here deposition of 3 layers of 2 micron thick PSG, that means thicker PSG film you deposit to produce 6 micron thick film. The PSG films here acts as phosphorus diffusion source into the sandwich polysilicon layer. PSG means phosphorus doped silicon glass. Okay. From there you can get the phosphorus diffusion in the underneath silicon layer. Then protection layer for subsequent bulk micromachining, that also because it is a insulating layer. So, subsequent bulk micromachining step it will act as a insulator, mask, as well as it will act as a diffusion source for subsequent diffusion. So, that is this step. Then we go for the etching of coating material. Etch coating is annealed for 1 hour for 1000 degree centigrade to drive phosphorus into polysilicon. So, from polysilicon phosphorus is driven to higher depth. To make a front to back alignment, and alignment windows is formed by patterning the PSG on the front side. Anisotropic silicon etching in EDP for alignment windows. So, these are alignment windows. So, silicon wafer is etched by EDP. So, now the last step here, patterning of break lines. So, because if you make many devices, you have to make a that is scribe line, basically break lines on the PSG around the silicon gripper area. These lines effectively prevent any crack in PSG membrane from propagating to the gripper arms. So, in many cases when you break, lot of micro cracks may appear, and those cracks sometimes propagate into a device and which will make the device not usable. So, that is why in many of these the microstructure devices, some of the breaking lines is etched, so that easily you can separate without drilling much into the substrate. So, that is why at the end step always some break line is etched, so that at the end you can easily separate those at those break lines, so that individual devices you will get it. So, in this way you can get the structure and you can separate it. So, like this, here you can etching of the sacrificial PSG film, time etch, overhanging polysilicon microgripper is exposed after full removal of PSG from top and bottom. All polysilicon conducting lines have a PSG layer left underneath them, which anchors them to the substrate. Okay. So, with this you will get the complete microgripper structure. Basically, the microgripper structures and the micromotor, stator and rotor at the same time fabrication, these two particular microstructure devices is not so simple. You have to give much more concentration to understand each layer, how the etching is taking place. So, by now I hope I have discussed many of the microstructure structures using surface micromachining process, which have got direct application in many of the devices. I will not continue the micromachining chapter, micromachining topics further. So, now onwards we will concentrate on microsensors and devices from next lecture. Thank you very much. So, we will discuss today on microstereolithography, which has not been covered in either your bulk or surface micromachining class, or you have not come across this particular topic in your VLSI technology course. So, this is a lithography, means basic principle of lithography is there. That means, you are getting some structure from mask level onto the wafer level, but here we will not use any mask. This kind of structure fabrication is without using any mask. So, that is why it is altogether a new and basically innovative technique of fabrication of various kinds of microstructure, which is being used nowadays not only in silicon MEMS, but also in polymer or ceramic or composite material MEMS. And in my last lecture on materials for MEMS, I told you that MEMS are getting fabricated nowadays not only out of silicon, but also from other materials like polymer materials, like ceramic materials, like metals and like composite materials and so on. So, if it is different from silicon, so that means that particular technology may not be compatible with the normal VLSI process. So, we can adopt some other technology, and there main emphasis is making or fabrication of microstructure, and later on this microstructure may be pasted or may be transported onto silicon wafer, but the microstructures are fabricated separately using a certain technique, and that particular technique is known as microstereolithography. The name stereo is there. As the name stereo, you understand that it will be 3-dimensional structure. So, normally the x, y and z in normal lithography or normal bulk and surface micromachining, there is a limitation on the thickness of the structure, means along the z direction the thickness of the microstructure or materials, there is a limitation. But here in this particular technique, which is known as microstereolithography, there that limitation is not there. So, you can have larger thickness material without any mask, without any micromachining by etching, that is output beam shape, and power available, that means it depends on the intensity, how much intensity is incident on the polymer. So, those things are all important when you make the complete system. Beam delivery elements are used to fold the path of the laser beam that compacts the SL system. Okay. Now, the layer preparation. The layer preparation means you have to have a very uniform layer of the resin or photoresist which are being exposed. Flat resin layer of the desired thickness is prepared for curing. The liquid resin surface will be the foundation of each layer of the SL model. SL system should satisfy the following requirements of the resin surface. What are the requirements? First is it should be uniformly flat, leveled and free from extraneous features. Second is it should maintain precisely at focal plane of the imaging system. The resin layer must be at the focal plane of the imaging system. That means, the focus spot where the beam is focused at a point, the whole layer should be in that particular plane. So, that there you will get maximum intensity. Surface must be a controlled distance above the previously built solidified cross section of the part. That means, previously built solidified cross section. It is a layer by layer preparation. So, a layer is prepared, it is exposed and it becomes hard. So, on the top of that again you are making another layer and then you are exposing that. So, that means the distance, that means you see the focused beam, the focusing plane remains same, layer is moving along vertical in z direction, is not it. So, in that way that has to be accurately controlled. So, that when the z moves, it should not, depending on the thickness of each layer, the z movement has to be adjusted. So, that complete layer will be in the focusing plane and within the region of the width of maximum intensity width. Okay. So, now that is penetration depth, which I call earlier penetration depth within that. Now, the recoating and leveling system work together to have a flat layer of liquid resin of proper thickness. Recoating and leveling, because layer by layer you have to recoat. After just recoating, then leveling has to be done. That is done again by electronic sensors. Now, here is one example to make movable gear and shaft. So, using the first method is a conventional MS. So, there you see some support layer is there. In the second one is the superized process, the gear and shaft is made without any support layer or sacrificial layer, just this beam spot is scanned vertically and laterally, and you can get this kind of structure. This is the comparison between IH and superized process. Now, the ceramic Emmechelle, ceramic microstereolithography, these are some ceramic structure you can see at the corner of the view graph. So, ceramic materials have useful properties such as high temperature or chemical resistance, high hardness, low thermal conductivity, ferroelectricity and piezoelectricity. Because of those properties, ceramic materials are used in some MEMS devices. 3D ceramic microstructures are of special interest in application such as micro engines and microfluidics. These are the two application areas of ceramic microstructures. Unlike conventional silicon micromachining, Emmechelle can be used to build the complex ceramic 3D microstructures in a rapid free form fashion without the need for high precision and high temperature. Here you have to use the additive process, because the ceramic material cannot be exposed and polymer chain reaction will not be there, it is not polymer. So, basically it is little bit different, and it needs at the end some curing process. The ceramic powders are mixed with polymeric material, and after that you have to have cured, and during curing process the polymeric materials will leave the will evaporate, and the solid ceramic you will get. So, the resin system for ceramic Emmechelle is composed not only of the monomer and photoinitiators that are used in polymer Emmechelle, but also of ceramic powders, what I mentioned, ceramic powders, monomers and photoinitiators. The photoinitiators are basically reacting with the optic system. Dispersants and diluents are used to obtain a homogeneous ceramic suspension with a relatively low viscosity. Upon UV polymerization, the ceramic particles are bonded together by the polymer and the ceramic body is formed. This is the complete ceramic Emmechelle process. So, with this let me stop here. I discussed the overall the stereolithography system and microstereolithography also, and extension of this method in the ceramic Emmechelle process to get ceramic microstructures. Thank you.